Hello. In this video, we're going to go through a couple more examples of mathematical induction. Now here are the statements we saw in class this morning. Each of these statements can be proved using mathematical induction, and we looked at the outline for such a proof. Now for the first two, we went through and we actually wrote down proofs for the statement. We didn't get to the third one, and we're not going to prove it, although if you're interested, the proof is very accessible, and you can find it by consulting various sources online. Here's a link that will take you to a proof. Maybe not written up as carefully as we will be writing up induction proofs in our class, but it has all the ideas of the proof. I hope you enjoy reading it. All right, now we're going to, in this video, take a look at a couple other examples. Now, like we saw in class, these examples can be sort of arrived at through patterns. And I want to get across the idea that you don't necessarily know what you're going to prove until you actually get around and start playing with it. This is the fun of math. But when you do find a pattern, that's when you ask, is there a proof? Can I prove this? So let's suppose for a second that we're just playing around with numbers of the form 4 to the 3n plus 8 for some reason that escapes us now. But if you do plug in the first few non-negative integers into this expression, you'll see that we get 9, 72, 4104, and 262,152. Now, the first ones are clearly divisible by 9. The next one has its digits adding to 9, and the next one has its digits adding to 18. And if you remember anything about divisibility rules from earlier school experiences, you might be able to tell that, yeah, each of these is divisible by 9. And so we might conjecture that maybe that's always the case. Is it always the case, and we think it is, that 9 goes into 4 raised to the 3n plus 8 whenever n is a non-negative integer? Now, this is a pattern we seem to notice, but we haven't proved it yet. On the other hand, if we take a look at another question, you might ask yourself, which is bigger, n factorial or n squared? Now, n factorial is something that you may or may not have run into in other math classes, but it's a pretty simple idea. N factorial just means take all the numbers from n all the way down to 1, n counting down to 1, and times them all together. So for instance, if I were to take a look at 3 factorial, 3 factorial is going to be equal to 3 times 2 times 1, and that will give me 6. 5 factorial is going to be 5 times 4 times 3 times 2 times 1, and that gives me 120. All right, now as you make a table and you start comparing the value of n factorial with n squared, you'll see that n squared starts off maybe with an early lead. But as we get around to the point 4 factorial is bigger than 4 squared, and the factorials really sort of take off. 5 factorial is a lot bigger than 5 squared. 6 factorial is 720, which is a lot bigger than 36. So we might conjecture that actually n factorial is going to be bigger than n squared for all n past the point 4. Now, we're going to be approaching these with mathematical induction. We'll notice that you can see that maybe induction will work because these are statements about all integers past a certain point. This first is a claim that we believe holds for all n past 0. And this second statement we believe holds for all n greater than or equal to 4. So because we have that pattern, induction is something that occurs to us to try. We're going to go through each of these in turn. So the first statement we're going to take a look at, we're going to use an induction proof. The outline is here, and here's what it looks like. We're going to start by announcing we're using induction. Then we'll use the base case, that first statement, the statement corresponding to 0. We're going to see and state whether the claim is true when n equals 0. Now it is, if you do put 0 in there, the expression over here simplifies to 1 plus 8, which is equal to 9, and 9 clearly goes into 9. So we verified the statement in the case that n equals 0. Now for our induction step, we're going to suppose that the kth statement is true. Now the statement we're looking at is this line here, and the kth version of that is 9 divides 4 raised to the 3k plus 8. So we're going to suppose that k is some integer and that 9 does go into the quantity there. This is supposing the kth statement. And remember, with induction, you want to take the kth statement and use it to prove the k plus 1th statement. Now, putting k plus 1 in for n in the nth statement up here, we see that this is what we want to prove. Now, this is what we have to work with. This is what we want to prove. We want to see how do we fill in the details. Now, one thing that you'll maybe note is that here we have a definition that we can make use of. We're saying that 9 divides this expression, and we have a definition for that. That just means that there is some integer that 4 raised to the 3k plus 8 is equal to 9 times that integer. Now, if we're going to show that 9 goes into this thing, there should also be some integer such that 4 raised to the 3 times k plus 1 plus 8 is equal to 9 times that mystery integer. Now, we're hoping that we're going to fill that expression, fill that blank in as we go along. But because we don't really know what else to do, let's just go ahead and play around with this thing. You'll note this corresponds to one part of the final statement. I'm not saying that 9 divides this just yet. I'm just taking that quantity and I'm going to sort of simplify it, doing whatever occurs to me. Well, as I look at that, I see that we have a 3 times a quantity in the exponent, so maybe I'll distribute that out. 4 raised to the 3k plus 3 plus 8. And then I know that I want to sort of connect back to this statement, I supposed, if I can. So I'd like to get the plus 3 away from the 3k. Now, you'll notice a property from exponents is being used here. Whenever you have an addition inside of an exponent, you can sort of turn that into multiplication outside of the exponents. And then if I simplify the 4 to the 3rd, that's 4 times 4 is 16, times another 4 gives us 64. All right, so this expression simplifies to 64 times 4 to the 3k plus 8. Now what I want to do is show this is divisible by 9, and that's not necessarily clear. I also have not used my induction hypothesis in any way yet, but I'm close. I have 64 times 4 to the 3k plus 8, and I could do something if I just had one of those 4 to the 3k's plus 8. I could substitute 9l in its place. Well, having 64, I can definitely use one of them and have 63 left over. So my next step is going to be to break the 64 times 4 to the 3k into 63 times 4 to the 3k plus one more 4 to the 3k. Now, because I've broken the 64 up in this way, I can take this 4 to the 3k plus 8 and substitute 9l in its place. And now we're hoping to get 9 times an integer. And now you can kind of see where that comes from. I have a 63, which is divisible by 9, and I have a 9l. And so if I were to factor a 9 out of each, I'd get 7 times 4 raised to the 3k plus l, which is clearly an integer. And therefore, this quantity we started with is divisible by 9. And that finishes our proof by induction. All right, now if you are practicing, what I would suggest doing, maybe, is if you haven't already, go back, rewind the video, and without looking at the answer, go ahead and try to prove this before watching the rest of the proof, and see how closely you can get your answer to look like this one without looking at any books or notes. Okay, now on the next example, same kind of thing. Before we go through the solution, why don't you pause the video now, go ahead and see if you can write down an induction proof now. All right, let's assume that you did that, and now let's take a look at an answer. To prove that n factorial is greater than n squared for all integers n greater than or equal to 4, we're going to start with our regular induction outline. Now you can kind of notice that there's going to be some sort of guesswork or scratch work off to the side here, so I've kind of made room for that already. But we're just going to start off assuming, like we normally do, that the induction outline will be profitable here. We're going to proceed by induction on n. The first thing to do is look at the base case. Now the statement Sn would be this inequality there. The base case would be the case where n equals 4. And so we're going to just notice that, yeah, 4 factorial is bigger than 4 squared, and here's why. It's because 4 factorial is equal to 24, and that's bigger than 16, which is 4 squared. All right, now with the inductive step, again, we're going to suppose that the kth statement holds for some k, and I want to show that the k plus 1th statement holds. using this fact that the kth statement holds. Now, how am I going to prove that k plus 1 factorial is greater than k plus 1 squared, knowing this? I'm looking for a connection between this statement and this one, and our factorials will do it for us. You'll notice here k plus 1 factorial and k factorial satisfy some kind of relationship. Now, to illustrate that, I'll do an example over my scratch paper. Notice that 4 factorial is 4 times 3 times 2 times 1. But if you think about it, 3 times 2 times 1, that's just the same thing as 3 factorial. So 4 factorial is equal to that extra 4 times 3 factorial, which accounts for the rest of the terms in the product. So likewise, if we're comparing k plus 1 factorial to k factorial, you'll see that k plus 1 factorial is defined as k plus 1 times all the numbers from k down to 1. But all the numbers from k down to 1, that's exactly what k factorial is. So k plus 1 factorial is k plus 1 times k factorial. Now I know this, and so maybe I can times both sides of the inequality by k plus 1. If I do that on the left-hand side, I'll create the k plus 1 factorial I'm hoping for. Now on the right, I'll have k plus 1 times k squared. So I know k plus 1 factorial is bigger than this, but what I really want is that k plus 1 factorial is bigger than this. And we're not quite there yet. Or are we? So we know that k plus 1 factorial is at least this big. And so over on the scratch paper, I'm going to ask myself, is it possible that we're done already? Is it possible that this thing, which I know I'm bigger than, is actually bigger than that thing? And therefore this thing is definitely bigger than that thing already? Is k plus 1 times k squared greater than k plus 1 squared? Well, if we try to think through that, you'll notice that we have a k plus 1 on both sides. So let's imagine that I didn't have that k plus 1 on the left-hand side, and I didn't have one of those ones on the right-hand side. I'd like to know, is k squared greater than k plus 1? If so, then I could take this inequality and times it by k plus 1, and I could get the one before it. And I could then finish the proof. Now, is this thing going to be true? Well, let's take a look at this. Let's do kind of a similar trick as on the line above. Let's divide both sides by k and just ask, is k on the left greater than 1 plus 1 over k on the right? You'll notice there I just divided both sides of this inequality by k. I'm just trying to see if I can explain why this should be true, and this is something I'm just trying for the heck of it. Now, here we've kind of reduced our inequalities just down to having a k, and that's helpful because look at what we already know. We know that k is greater than or equal to 4, and that's going to help us answer this question. And you'll see that, yeah, actually, since k is greater than or equal to 4, k is definitely bigger than 1 1/4, and 4 is being less than k. 1 over k as a fraction is going to be less than or equal to 1 over 4. And so I can definitely explain why k is greater than 1 plus 1 over k. Now, timesing both sides of this expression by k, I'll get the inequality k squared greater than k plus 1. And timesing both sides of that one by k plus 1, I'll get this expression there. You'll notice that I'm kind of following the opposite order of steps that I was working here or on my scratch paper. Now, doing that, I gave a reason why these inequalities should be true. Now I know that k plus 1 factorial is greater than k plus 1 times k squared, and I just got done showing that k plus 1 squared was k plus 1 times k squared was greater than k plus 1 squared. So once I put those two facts together, I get that k plus 1 factorial is greater than k plus 1 squared, and my induction proof is over. Alright, so this example was a bit more complicated. We were working with inequalities, which is the first time we've seen an example like that, and you'll notice that it wasn't quite clear what to do. With inequalities, you often do have to do a little bit of work on scratch paper, trying to see why something should be true. But please take a look at these two examples, look over them and study them as you try to work through your own induction problems, and let me know if you have any questions. I'll see you in class.